Hello everyone. Well, in the last lesson we finished seeing all the memory elements, all the bytes table we are going to use in the subject, and we had 4 memory elements, 4 bytes table. I told you that the thing that you have to learn by heart is the behavior table. The behavior table was the bytes table do with the net state according to the value of the input of the bytes table. So you are going to have 4 behavior table, 1 for each bytes table. In the case of the SR, we have that we can keep the current state for the net state, we can reset the net state with a 0, or we can set the net state with a 1, and these inputs were not allowed. In the case of the T bytes table, we have this behavior table that is quite simple. We have only one input, so we can decide either if we can to keep the current state in the net state of just negating the current state in the net state. Remember that the T from the T of the T bytes table comes from the word in English toggle, and toggle means alternate. So when a 1 in the input of the bytes table, we are going to toggle the value of the current state for the net state. In the JK bytes table, we have 2 inputs, and this bytes table was a mix between the SR bytes table and the T bytes table. We can decide if we want to keep the current state in the net state, if we want to reset the net state, we want to set the net state with a 1, or we want to toggle to complement the current state into the net state, and this behavior, the toggle, comes from the T bytes table. So we have 3, and the last bytes table is the D bytes table, and this is its behavior table. This is the simplest bytes table we are going to have, because if we look at the input of the bytes table, the only thing that this element is going to do is put a 0 in the net state if the input is 0, or put a 1 in the net state if the input is D. So with these 4 behavior tables, you are going to be able to obtain all the rest of the table that you need for the design of a sequential circuit. So once we saw all the bytes tables and how to obtain the circuit using different bytes table as memory element, I told you that at that point we have all the tools to do the analysis of a logic circuit that is a sequential circuit. We know already how to obtain from the logic circuit the transition table, the state output table, and from the state output table the state diagram. And the state diagram is going to be the equivalent to the truth table of a combinational circuit as the ones that we saw in topics 5 and topic 6. But if we want to design a sequential circuit starting with a specific needs, for example from a customer, we have all the tools but these 2. We need to learn these 2 tools. In the last lesson we see the state reduction. The state reduction was a method that we apply once we have the state output table. In the state output table, you know that we have in each cell what is going to be the net state from the current state for a specific input, and what is going to be the net output for the current state a specific input. So in this table we can check if we can reduce the number of states, and the equivalency is that we remove some of the rows of the table. So if we reduce the number of states, maybe we can have less memory elements. You remember that the state of the system has to be codified with zeros and ones. For example, if we have 8 states, we are going to need 3 state variables. 2 raised to 3 is 8, so with 3 state variables we can codify 8 states of the system. For example, if we go from 8 state to 4 states, if we are able to get only 4 states, we may use only two state variables. If we use fewer state variables, we can remove the numbers of the memory elements. Remember that each memory element is going to store the value of a state variable. So if we remove one state variable, we are going to remove one memory element, but also the logic gate that the memory element has at its input. Remember that for each sequential circuit, we are going to have here the memory elements that is specified in the exercise, and this combinational circuit, these logic gates, that we are going to design. In this case, was just an inverter, but in other cases, can be more complex. Here we have two AND gates, and we are going to see examples in which this combinational circuit is complex. So if we can save as well the combinational circuit, we are going to save a big cost in the design of the circuit. So the next tool that we have to learn is the assignment rules. I told you that the step from the state output table to the transition table is just to write in the table the net state, but using zeros and ones. Here we are going to codify the state. We are not going to use anymore A, B, C, D, or Q0, Q1, etc., but we are going to use zeros and ones. So far, we have used assignments, with no specific rules. Normally, we use a consecutive order. So if we have, for example, for a state, we have used 0, 0 for the first, 0, 1 for the second, until 1, 1 for the last state. But I told you that it's not. We have a rule to do that assignment. You may wonder what happens if we do a right assignment of the codes to the state. If we do a correct assignment, we're going to reduce the combinational circuit before the memory element. This combinational circuit is going to depend directly of the code that we assigned to the states from the state output table. So we are going to minimize, once we have the minimum possible number of memory elements, we are going to try to do this sequential circuit in the input of the memory element. We are going to try to make them as little as possible. We have here two algorithms for the analysis of sequential circuits and for the design of sequential circuits. We are going to use these slides in the exercises to verify that we are completing every step. But before, I told you that I need you to understand these two tools that we have to apply in the design of a sequential circuit. The first one was the state output table reduction, and we saw this in the last lesson. We look for compatible state, and I told you that if we have two states that are compatible, that situation in the circuit can be covered just by a single state, so we can reduce the number of states of the table. So our goal here is to have as few states as possible, and we have to apply these two conditions, A and B, and we have to meet the two conditions, not only one of them. This is an AND condition, the A and the B. So two states are going to be compatible if the output is the same for all the inputs, and two states are going to be compatible if their net states are the same. If we see this in two rows of the state output table, these two states are going to be directly compatible, so we can remove one of them. If we don't have this in the table, that the net states of the two states are the same, we have to check the second condition. They may be also compatible, and this condition is more difficult to see. So I told you that we have a method to compare directly all the states of the table, and this method was the implication chart. We apply the implication chart. Here you have the method explained, but I explained you the method with an example. And in our example, we have this this state output table and we apply the method of the implication chart. We obtain this implication chart. I told you that we have to start doing passes through all the cells of the tables. And when in the current pass we cannot add new X in the cells, we have finished. Once we have finished, the cells that have no X are going to be the cells of the compatible state. So here we saw that here we don't have X, here we don't have X, here we don't have X. So the state 1 and 3, that is the state corresponding to the cells, are compatible. The state 3 and 4 are compatible, and the state 5 and 6 are compatible. And we have this one. When we're filling the table, we cannot add any condition, any dependency to a cell. It means that these two tables are compatible. So we have compatibles, the 1 and the 3, the 1 and the 4, the 3 and the 4, and the 5 and the 6. We have them here. The next step was to obtain the maximum compatible set. That is to group in set all the compatible states. We can see that 1 is compatible with 3, 1 is compatible with 4, and 3 is compatible with 4. So 1, 3, and 4 are the three of them compatible state. So the maximum compatible set was 1, 3, and 4, 5 and 6 that are compatible between them but not with any other state, and the state 2. The state 2 was incompatible with the rest of them. So this is a state that cannot be reduced. We have to add this state. So now we are going to see the last tool to minimize the circuit. And once we see this tool, we have finished all the contents of the topic 7. So from this point on, we are going to do just exercises of analysis of sequential circuit and exercises of design of sequential circuit that are going to be mainly the two things that we are going to do in topic 7. You may wonder why this assignment of just binary numbers to the state variables, is so important. How this may affect to this combinational circuit, because it's weird in the beginning if we think about it. So I'm going to show you an example of just having a circuit, having an exercise, a design, and we are going to use just consecutive order, correlative order to assign the binary numbers to the states of the system. Here we have this example in which we start with the state output table. Here we have the output, but I didn't write the output because we are not going to use the output in this example, just to avoid having so many information in the screen. You know that the first step is to obtain the state diagram from the specification of the exercise, etc., and the arcs with the transitions. And once we have this, the next step is to obtain the state output table. So we are going to start in this step. Here we have 6 states where we are going to consider that the states in this exercise are 1, 2, 3, 4, 5, and 6. We may have used A, B, C, Q0, Q1. It's a decision of us. It doesn't matter. We can use the method we want to name this state. In this example, I have used from 1 to 6. So once we have the state output table, we should reduce the number of states. In this example, I'm going to tell you that the state output table cannot be reduced any longer. So we are going to consider that this state output table is minimum. Okay. So in order to obtain the transition table, we have to codify with binary code the states. Well, the transition table is just the same as the state output table, but removing the outputs and using the code, the binary code of the state. It's just copying this table here using the assignment, the binary assignment we have used for the state. In this example, I have used correlative order. So if I have 6 states, I have used 0, 0, 0, 0, 0, 1, 0, 1, 0, just increasing the binary number of the table. So I have used from 0, 0, 0, from 1, 0, 1. It may seem logic, I mean, why not? So we write now the transition table, looking at the state output table. Okay? So from state 1, with the input 0, we go to state 4. State 4 is 0, 1, 1. So I write here 0, 1, 1. And from state 1 and input 1, the next state is 3. And 3 is codified with 0, 1, 0. So I write in this cell 0, 1, 0. For state 2, the next state with the input 0 is 6. 6 in the table is 1, 0, 1. So I write 1, 0, 1. For state 2 and input 1, the next state is 3. So 3 is 0, 1, 1. 0, 1, 1. So we continue just filling the table using the codification we have decided for every state. And since we have 3 state variables, because if we have 6 states, we need 3 state variables. Sorry. Why? This is quite simple. With 2 state variables, we can codify 4 states, but we have 6. So we have to use 3 state variables. This is here a 2. So with 3 state variables, we can codify until 8 states. And we have 2 combinations that are free. In these 2 combinations, we write X that we can use as don't care condition to make simpler the minimization of the Karnaugh maps. So we continue. Once we have the transition table, I told you that we have the most important step in the design of a circuit, that is obtaining the excitation table of the circuit. To build the excitation table, we need the transition table and the evolution table. I told you that we need the transition table of our design. This is the target, the circuit that we have to build, and the evolution table of the memory element that we have to use as basic block to build this sequential circuit. In this exercise, we can suppose that we have been told that the memory element that we have to use compulsorily is the bistable D. So we have here the evolution table of the bistable D. I told you that the bistable D was the simplest one, because in fact, if we look at the evolution table, if we have a 0 and the next state is 0, the input of the bistable is going to be 0. If we have a 0 and the next state is 1, the input of the bistable has to be 1. In fact, the inputs of this bistable is going to be always the value of the next state we need. So the current state doesn't matter. This column doesn't matter, okay? Because we are just looking on here. The input of the bistable D has to be the value that we want for the net, for the net state, and the current state doesn't matter. So we are going to to fill the transition table. Well, it's already fixed, it's already filled, but I'm going to explain to remember how to fill this table. So if the net state is 0, sorry, if the current state is 0 and the net state has to be 0, the value in the input has to be 0. So we write here a 0. If the current state is 0 and the net state is 1, we have to choose the input 1 in the base table. So if you look at the table, in fact, you can see that both tables are the same. Because in the case, only in the case of bistable D, the input is going to be equal to the value of the net state. So in this table that we have the input, we can copy the value of the net state. In order to have a specific net state, we have to put in the input the value of that specific net state. So if you look at all the cells, we have the same value. So only in the case of the bistable D, you can save one table, because the transition table and the excitation table are going to be the same, just because of the behavior of the bistable of this. The input is exactly the same as the value of the net state. So we can copy the table. So once we are here, we just has to build the Karnaugh map for all the variables or the input, all the bistable. If we have 3 state variables, we are going to need 3 memory elements. These 3 memory elements are going to be one bistable D, another bistable D, and another bistable D. And they are bistable D because we have supposed that in this exercise we have to do it with bistable D. So I'm going to extract the Karnaugh map of this excitation table to obtain the function that is going to be in the input of each bistable. So the last step, the last stage of the design, is to build the Karnaugh map from the excitation table and to obtain the logic function that we have to put in the input of the 3 bistable. We are going to build the Karnaugh maps, as we saw in the design of the bistable, using the excitation table. So in the excitation table we have 3 variables at the same time. It's quite difficult to obtain from that the minimum function for D1, D2 and D3. So I have built 3 Karnaugh maps and I have filled them using the excitation table. And now we are going to obtain the prime implicants of all the Karnaugh maps, and we are going to obtain the logic functions of D1, D2 and D3. If you have doubts of how I fill the Karnaugh maps using the excitation table, we are, for example, we are going to explain how I did it with the first Karnaugh map with D1. So in the Karnaugh maps we are going to have 4 variables because we have one input that is X and 3 state variables Y1, Y2 and Y3. So we are going to use all these variables in the output of the Karnaugh map. So for example, if we are here in this column, I'm going to use colors. If we are here, we can see that X is 0 and Y1 is 0. So just let me fill this value that I don't know why it was cleared. I continue. So as I was saying, if we are here, we have that X is 1 and Y is 1. So in the excitation table, X is 0 here and Y1 is 0 here. So we are for the variable d in these values 0, 1, 1, 0. So I fill the kernel map 0, 1, 1, 0. And remember that I use this order because of the gray code we have here, in which we have the 1, 1 before the 1, 0. So in the second column, x is 0 and y is 1. X is 0 in the same column, but y is 1 here in the following rows. So the value of d1 in those cases is 0, 0, x, x. So I fill the kernel map 0, 0, x, x. In the case in which x and y1 are both of them 1, we are here. X is 1 here and y1 is here in these rows. So the value of d1 is going to be in those cases 0, 0, x, x, 0, 0, x, x. And finally, we are in the case in which x is 1 and y1 is 0. X is 1 here in this column and y1 is 0 in these rows. So we copy the values of d1 0, 0, 0, 1, 0, 0, 0, 1. And now we repeat the same steps, but using for d2 the values here and so on, and for the value d3 using the third value that we have in the cells. So once we have all the kernel maps, we are going to minimize the function. So for example, here in the kernel map of d1 we have this prime implicant, this prime implicant, and this prime implicant. So if we call this implicant 1, implicant 2, and implicant 3, we have here implicant 1, implicant 2, and implicant 3. And this is the expression of d1. For the case of d2, we have this prime implicant, we have this prime implicant, and we have this prime implicant. And we can call them, for example, implicant 4, implicant 5, and implicant 6. So we have here implicant 4, implicant 5, and implicant 6. And finally, in the D3 kernel map, we can find this prime implicant. Sorry, I moved this. This prime implicant and these two prime implicants to cover the kernel map. We can call this implicant 7, implicant 7, this one, for example, implicant 8, this implicant 9, and this one implicant 10. So we have here implicant 7, implicant 8, implicant 9, and here implicant 10. So the next step would be just to finish the exercise to draw the logic circuit. So we should let me delete this. Well, I just let me to to clear the kind of map because I need space. So the next state that I'm not going to do completely to save time is to have the 3 d by stable. We need 3 because we have 3 state variables. We are going to have here I1 negated, Y2 negated, it's okay, Y3 and Y3 negated. Remember that in the bistable we are going to have always the state variable and the state variable negated. Here we are going to have D1, here D2, and here D3. And before D1 we have to implement this expression with, we have here OR and ARM gates. Before D2 we have to implement this circuit, and before D3 this combinational circuit. So here we have combinational circuit 1, combinational circuit 2, and combinational circuit 3. And this is what we obtained using, this is important, using this assignment of the binary codes to the states. Now we are going to repeat the same exercise by changing the assignment that we use to codify the step. We are going to see if we can make a difference here, if this can be simpler or more complex. Just let me clear this and we continue.